Okay, hello everyone. Good morning, all of you. Sorry, good afternoon, I have to put, I think. Okay. So today we'll start with a quote. I have learned it's important not to limit yourself. You can do whatever you really love to do, no matter what it is. Okay, that is more important. As I told many times, the passion is important. If there is passion, there is no limit for whatever you do. Okay, so the main requirement is the passion. And I think we missed it. Okay, I think we missed it. What the birthday for today? Actually, I have noted. Okay. Okay, we'll just recollect whatever we had done in the last class. So last class we have discussed about the detailed syllabus, chapter wise, and then the course outcomes, then scheme of evaluation, then we have seen what are the textbooks and okay. So today I will send you the detailed syllabus, lecture schedule, the textbooks, reference books, all these things. Today I will send you. And then we started about what is classification of thermal machines. Okay, we classified them as incompressible and compressible. Sorry, first we have done work absorbing and work producing, and then we started here as incompressible and compressible, and then we have positive displacement and turbo machines, and here reciprocating and the rotary, and again we have put like gear pump, screw pump, vane pump, like that. And here we made it as closed and open, like we have ship propeller here, and closed we have centrifugal. Some things I am missing, just I am putting fast, so mix it like that. Okay, in the same way we have started with the compressible side, and the compressible side also we have positive displacement and turbo machines. In the positive displacement again we have reciprocating and rotary, like that. Okay, and in turbo machines we have closed and open. So here ceiling fan, propeller, like that we got. And in the closed again we have centrifugal, axial, mixed, and also we have another like fans, blowers, compressors, like that. And then we have gone to work producing machines, and again we have classified them into positive displacement and turbo machines. And positive displacement we got what are called as IC engines, and we classified them as again reciprocating and rotary. And the reciprocating we have SI, CI, and then 2-stroke and 4-stroke, like that. And coming to turbo machines, we have put like incompressible and compressible. And here we got what are called as hydraulic turbines. And we got here Pelton, uh, Francis, Kaplan, like that. And coming to compressible one, we have again closed and open. And we got windmills here. And in the closed, we got two phase and single. All are there?
Yes, sir.
We lost connection in between. Huh?
Yes, sir.
When did we lose connection?
Sir, in the clo- closed ones.
So,
After fan blower or compressor, sir, the last
okay.
when
Okay, these things, work producing machines, have you seen this?
Sir, please share again the screen, sir.
Yes, sir.
Oh, okay, okay. Sorry. Can you see the screen now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now, so in this, you are seeing this fans, blowers, and compressors, right? So
Yes,
the
sir.
next one, have you seen this for producing machines? Okay, just I
Sir,
will.
in compressible up to closed we showed.
Okay, so this is incompressible, this closed open ship propeller, and in the closed centrifugal axial and mixed. And in the compressible side, we have positive displacement and turbo machines. In the positive displacement, we have reciprocating and rotary. In the turbo machine, we have closed and open, which is fan and propeller, that is aircraft propeller. And the closed, we have centrifugal, axial, and mixed. And here it can be also another classification, fans, blowers, and compressors. Okay, this is on the work absorbing side. And work producing side, it is like this positive displacement, which are IC engines and again turbo machines. In the IC engines, we have that is positive displacement engines. We have reciprocating and rotary. Rotary is Wankel engine we have discussed. And in the IC engines, we have SI engine and CI engine. And in the SI and CI, we can have two-stroke and four-stroke engines. Okay, and that's why if you in between, if we have a little bit interaction, I will know that you are there or connection is gone or whether you are there or not. Okay, in turbo machines, we have incompressible and compressible. Incompressible means hydraulic turbines. In the hydraulic, we have Pelton, Francis, and Kaplan turbines, right? And on the compressible side, we have closed cycle or closed machine or open machine. Open machine is windmill, and closed machines, we can have two-phase machines or single-phase machines. And two-phase machines means steam turbines. And steam turbines can be impulse reaction or impulse reaction. And in the impulse, it can be single stage or compounding. In the compounding, we can have velocity compounding, pressure compounding, velocity pressure compounding like that. Okay, this is on the steam turbine side. And coming to the single phase side, gas turbine side, which we are interested as I told. So gas turbine side, we can have open cycle or closed cycle, and closed cycle is Joule cycle. In the open cycle, you can have constant volume combustion or constant pressure combustion. And constant volume means Atkinson cycle, constant pressure is Brayton cycle. And in the Brayton cycle, we have various things like simple cycle, intercooling cycle, reheating cycle, heat exchange cycle, and combination of all of them. Okay, so these things we are going to discuss later. Okay, so that's what we have discussed. And then what I am talking about is about the evolution of the universe. Okay, this is where I am asking questions actually. Okay, at the beginning, what is there at the beginning of the universe?
Big Bang.
So there is initially a point mass, right? Everything is there, and so then there is Big Bang. Okay, that is at the beginning of the universe, and it started expanding, and slowly the fundamental forces started evolving. Evolving or emerging, right? So what is the first fundamental force we get is gravitational force. Okay, and then we have what is called as strong nuclear force. Okay, gravitational force is the force between all celestial bodies and all. And what is strong nuclear force? Anybody knows about it? So this is a reason for formation of protons, neutrons, nucleus, and all, right? And protons and neutrons are formed by quarks. And a proton is equal to 2 up quarks plus 1 down quark. And neutron is reverse, right? Neutron is equal to 1 up quark and 2 down quarks. Okay, so these quarks are bound together by strong nuclear force, and they form protons and neutrons. And these protons and neutrons also are bound together to form nucleus. Right? So the reason of binding of these two together is the strong nuclear force. And then came what is called as weak nuclear force, which is a reason for radioactivity and all. Okay. And so electrons come into picture now. Now the force to keep nucleus and electrons together is called as the fourth force. What is that force? Electromagnetic force. Okay, so these are called as the four fundamental forces of nature. One is gravitational force, and then strong nuclear force, and weak nuclear force, and the electromagnetic force. Okay, so the theory, the science that deals with the general theory of relativity by Einstein. And strong nuclear force, quantum electrodynamics. And weak nuclear force, this is actually electroweak theory. And the theory is quantum chromodynamics. And the particles that deal with this is, we know that these are photons. Photons are the particles due to which the electromagnetic forces exist. In the same way, we have what are called as gravitons for gravitational force, and we have these are called gluons, and these are called bosons, W bosons, Z bosons, like that. Okay, these are the particles through which these are called as mediators. And the weakest force is gravitational force. If this is of the order of 1, okay, so the electroweak force, that is nuclear weak force, this is of the order of 10 power 25. And electromagnetic force is the order of 10 power 36. And the strong nuclear force is the order of 10 power 38. Okay, so these are the four fundamental forces people call it as. And actually this electromagnetic force also is unified electric plus magnetic force. So this is unified by Faraday. Now people wanted to unify all these four theories, over the four forces, which the science is called as grand unification theory. And this is also called as theory of everything. There are books available with the title theory of everything, like that. Okay, this grand unification theory, it is a lot of work is done on this. And there is one Pakistani scientist called as Abdus Salam. He got Nobel Prize in 1979. So he has unified these three forces also: electromagnetic, strong nuclear, and weak nuclear forces. Only thing is, still he could not unify gravitational force. If they could combine that also into this, so we call it as grand unification. There is only one primary force, and these are the secondary forces, like that they can come. They wanted to do that. So for this only, they use what are called as particle accelerators. You might have come across about this name of particle accelerators and particle colliders. So they are spending millions of rupees for this. Actually, the underground, they construct huge tunnels. Okay, so they accelerate the elementary particles, and they wanted to make them collide and see what happens. And through that, actually, they wanted to do this unification. Okay. These are something about I wanted to share about the universe evolution and all. Now coming to our subject, we are talking about what are called as air standard cycle or ideal cycle assumptions. So yesterday we are talking about this. One is air is considered to be perfect gas. Perfect means ideal gas, and Cp and Cv are
Constant.
okay. And then compression and expansion are
Isentropic.
isentropic. That is friction negligible. And then heat transfer, heat addition and rejection are through heat exchange process only. Means no combustion within the working fluid. Means composition of working fluid is constant, and also mass flow of the fluid is constant. Because otherwise, if fuel burns inside, there will be increase of the mass of the working fluid. Okay, so that is that. And and the heat exchange process is isobaric, no pressure loss. Because normally in heat exchangers, because it flows through pipes for long distances, like in different loops and all, so there will be pressure losses, and we assume, and no pressure loss in piping also. And no transmission losses. That is turbine to compressor, and turbine to generator. Okay, and then complete combustion takes place. And next, another thing is heat exchange process is effectiveness is equal to 1. Okay, so the that is one loses heat, one gains heat. The difference in temperatures, or the heat lost is completely taken by heat the other one. So then this is called heat exchange process 1. Okay, so these are the various assumptions we make. So we go to what is called as ideal.
Sir,
Yes. Ask me.
sir, one side is we are saying like heat exchange. We can say there is no combustion taking place, and the other side we are saying like complete combustion taking place. So how?
No. Actually, okay. If there is combustion, okay, combustion, I should not talk about it. But if you want to know what is the input, combustion is taking place from outside, and that heat is transferred through heat exchanger. Okay, so that combustion, I assume it is complete combustion, but it is not there in the cycle. Okay.
Okay, sir.
Right. Thank you. So ideal Brayton cycle which is actually Joule cycle. So that is, I am assuming it to be closed. Okay. And so this is, I assuming it external combustion and closed. Okay. So if I draw a schematic, so I will have a compressor. The air enters here like this. This is state 1 and this is compressor, and then it enters the, okay, here I have to put heat exchanger where I will have heat addition, and okay, this is to be run by a compressor which takes a work of WC. So here there is a turbine, and this goes here, and it produces total WT. If it produces WT minus WC goes, sorry. Okay, WC goes this side, and this side WT minus WC goes, which runs the generator. And here there will be another heat exchanger. Okay, so here there will be heat lost, and this is air cooler, and this is air heater. Okay, so this is the Joule cycle. But if you draw a Brayton cycle, actually how it should be is, this is combustion chamber, and this is left out like this, like open cycle. Okay, so this will be Brayton. This is compressor, combustion chamber, turbine. But okay, in the books, they will draw this only, and we call it as Brayton cycle. Okay, the ideal one, which is Joule cycle, is talked as Brayton cycle. Or sometimes they draw this only, and but they do the analysis like a closed cycle. Okay, when I draw a graph, right? If I draw a TS diagram, Brayton cycle, we'll get like this. Okay, so they draw this graph only, and they show this. Okay, 1 to 2. So this is 1, this is 2. 1 to 2 is isentropic compression. And 2 to 3, isobaric heat addition. So this is 2 to 3, isobaric heat addition. And 3 to 4, isentropic expansion. 3 to 4 is isentropic expansion, and 4 to 1 isobaric heat rejection, like this. So here it is just left like this only. It is open, but we call it as sometimes Joule cycle only, but this I will show it as closed. Okay, so it is left to you. Brayton and Joule cycle, they are interchangeably used, but we are discussing about the Brayton cycle, because that is the practical cycle, open cycle. Okay, Joule cycle, as I told, we use only in nuclear power plants. Okay, and this is the way the cycle takes place, and we will see some math part of it. This is 1, 2, 3, 4. WC, WT, QH, QL. Okay, and another assumption I forgot here: the change in kinetic energy and change in potential energy is neglected in all the processes. So this is also the another assumption. Okay, it's an important assumption. Okay, so if you take the first law of thermodynamics, for flow process. So what will you get? Okay, delta Q dot is equal to or I'll put in dH plus d of K plus d of P plus delta W. Okay, so this is the first law in watts. Okay, so if I integrate this, we get Q dot is equal to m dot into H2 minus H1 plus okay C2 square minus C1 square by 2 plus G Z2 minus Z1 plus W dot watts. Okay, so but here we are neglecting these two, and we get Q dot is equal to m dot into instead of H2 minus H1 I will write He minus Ha plus W dot. Okay, E is exit and I is inlet, because 1 2 for one process, and it can be 1 2 2 3 3 4 or 4 1 whatever it is. So this is the generalized one, watts. And if I take per unit mass, small q I will write here m dot I cancel plus W kilojoule per case. It is per unit mass flow. Okay, this is the generalized equation for all the 4 processes. But here during compression and expansion, Q will be 0. And during heat addition and heat rejection, W will be 0. So only one of Q or W exists. Okay, so if one of them exists, the other one is equal to change in enthalpy. Okay, so that is the way easy to remember. Okay, change in enthalpy is equal to work transfer or heat transfer in the respective process. Okay, now if we write WC compressor work is equal to H2 minus H1, and heat addition QH is equal to H3 minus H2, and WT turbine work is equal to H3 minus H4, and heat lost is QL is equal to H4 minus H1. And because it is a cycle, W net, the network is equal to, so what is the output? WT minus WC. And for a closed cycle, the net heat transfer is equal to net work transfer. Okay, so this is also QH minus QL. Okay, so like this I can write, and you can check actually. WT is H3 minus H4 minus H2 minus H1. This is also equal to H3 minus H2 minus H4 minus H1. So you will get a similar expression, right? Both will be same. This is network. And then what is efficiency? Efficiency is equal to
So network output by heat input.
network output by input, right? Right. Network by input, W net by QH. So this can be written as QH minus QL by QH, or 1 minus QL by QH. Okay, there are various ways you can calculate each one, and you can get it. Okay, because it's a perfect gas, H is equal to CPT. Okay, So WC is equal to H2 minus H1 is equal to Cp into T2 minus T1, and heat supplied is equal to H3 minus H2, which is Cp into T3 minus T2, and Wt is equal to H3 minus H4, that is Cp into T3 minus T4, and QL is equal to H4 minus H1, that is Cp into T4 minus T1. And so efficiency is equal to, you can write W net by QH, or Wt minus Wc by QH, or I can write QH minus QL by QH, or I can write 1 minus QL by QH. Okay, and so I can write this as 1 minus QL is Cp into T4 minus T1 by QH is Cp into T3 minus T2. Right. Okay, here some parameters for the cycle. So one is this T1 is constant. Okay, that is input condition. And this T3, actually this T3 also we cannot vary much, because this highest temperature is limited by the temperature limit of the material of the turbine. Okay, and what is this called as? That's why it is called as metallurgical limit. T1 is inlet temperature, and T3 is turbine exit temperature. This is also called as metallurgical limit. Metallurgical limit. Okay, and the other one is the parameter we introduce, and one parameter I'll put it as small t, which is T3 by T1. Okay, maximum temperature by minimum temperature of the cycle. Minimum temperature of the cycle. And the other one is the pressure ratio. So we will introduce R is pressure ratio, which is because it is working with two pressures. One is maximum pressure and another is minimum pressure. So P2 by P1. This is compressor pressure ratio. And this is also equal to P3 by P4, which is turbine pressure ratio. Is it clear? If you see this, so this is constant temperature, the pressure, P2 and P3, and P1 equal to 4, P4, this is isobar, okay? Like this. And from the isentropic relations, and what are the isentropic relations? Okay, sorry. And PV power gamma equal to constant. Okay, and so P1 V1 power gamma equal to P2 V2 power gamma. And also we can use equation of state, and using these two, you can relate the pressure ratio, temperature ratio, and volume ratio. So T2 by T1 is equal to P2 by P1 to the power of
Gamma minus 1 by gamma.
Gamma minus 1 by gamma. Okay, so this is important. So this, so T2 by T1 is equal to R power gamma minus 1 by gamma. The temperature ratio for the compressor is equal to pressure ratio to the power of gamma minus 1 by gamma. In the same way, this is for compressor, and for turbine, T3 by T4 also, which is equal to P3 by P4. P3 by P4 is P2 by P1, right? So this is also R power gamma minus 1 by gamma only. So what we get is T2 by T1 is equal to T3 by T4. Okay, we try to use that here. Okay, efficiency we got as 1 minus T4 minus T1 by T3 minus T2. Okay, and divide the numerator and denominator by T1. So this will become 1 minus T4 by T1 minus 1 by okay, all these things I not needed actually. Okay. Just
So T3 will be divided by T2, sir.
yeah. Actually, yeah. Numerator, what I'll do is T1 I take common. I will write it as T4 minus T1 minus 1. In the denominator, T2 I take common. So T3 by T2 minus 1 like this. Okay, so here if you see T4 by T1 is equal to T3 by T2 if I rewrite this. So this T4 by T1 minus 1 and T3 by T2 minus 1 will get cancelled. So I will get 1 minus T1 by T2. And from this, okay, so 1 minus, if I reverse this, 1 minus R power gamma minus 1 by gamma. So eta is equal to 1 minus 1 by R power gamma minus 1 by gamma. So this is the efficiency. Okay, so these things you know it, I am doing just a little bit quickly. And this R power gamma minus 1 by gamma is given another name, some C. So this will become 1 minus 1 by C. This small t and C are cycle parameters. So you have to be used to this particular terminology. I use some that small t and C very often. Okay. Okay, now I have efficiency is equal to 1 minus 1 by R power gamma minus 1 by gamma, that is equal to 1 by C. Okay, it's a function of, so efficiency is a function of R and gamma. And so if you give, if I take R here, so when R equal to 1, efficiency is 0. So here, this is 0. And as R increase, R power gamma minus 1 by gamma increase. So 1 by R power gamma minus 1 by gamma decrease. So 1 minus something decreasing will be increasing. So as R increase, efficiency increase as R increase. So it will come something like this. So as R increases, the pressure ratio increases, the efficiency increases. So this is one important observation. And not only that, efficiency is function of gamma also. Okay, so efficiency increases as gamma increases also. So you can put some two values for gamma and you can see. So if I take this air, gamma equal to 1.4, I can use some other fluid, like a gas, right, which is having higher gamma, and see what happens. Okay, so actually if I put helium, okay, gamma of air is 1.4 and gamma of helium is 1.66. So if I put that, I will get higher values for helium. Okay, as gamma increases also, the efficiency increases. Okay, but okay, now we are talking about air only as the working fluid. Why I am telling this is when I talked about closed cycle. So in the closed cycle gas turbine, if I can replace air by helium, I can increase the efficiency. Am I clear about it?
Yes, sir.
Okay. Now, this is about efficiency. But what about work? Okay, what happens to work and how it depends on the temperatures ratio and the pressure ratio. We'll see that. Okay, so W net, which is equal to WT minus WC. WT is Cp into T3 minus T4 minus this is WC is WT2 minus T1. Okay, and usually whenever we try to compare some things, we like to have non-dimensional values. So previous graph also between efficiency and pressure ratio, which are non-dimensional. So I want to get this to be non-dimensional. So what I do is I divide this by CP/T1. CP is constant and T1 also is a constant. So I want to divide this by CP/T1. So what will happen? I will get T3 by T1 minus T4 by T1 minus T2 by T1 minus 1. Okay, so I want to express this as a function of T and C. So how can I do that? What is T3 by T1?
T, sir.
T, sir. T, sir.
Okay, and T2 by T1? Small c. This is okay. And how can I write T4 by T1? So T4 by T1, I will write it as T4 by T3 into T3 by T1. Okay. And what is T4 by T3? T3 by T4 is C. T2 by T1 is equal to T3 by T4 is equal to C, right? So T4 by T3 is 1 by C. And T3 by T1 is T. Okay. So T minus T by C, like this. So I will write this as T into 1 minus 1 by C minus C minus 1. Okay, this is non-dimensional network. And always remember, I use this again. This is non-dimensional WT. This is C minus 1 is non-dimensional WC. Okay, this is turbine work and this is compressor work. Okay, this is network. And now I want to see, now this is a function of T and C only, right? So I want to see how this varies with T and C. And so now W net by CPT1 is equal to T into 1 minus 1 by C minus C minus 1. Okay, W net by CPT1. So when C equal to 1, what happens?
It will become 0.
0. Network is 0 because pressure ratio is 1 means P1 equal to P2. So it's not compressing at all. So that is 0. So this is 1. So there is another point where this network will become 0. What is that point? So if turbine work is equal to compressor work, actually initially that's what used to happen. What happened at the beginning of the research on the turbine is because of frictions and the low efficiencies of turbine and compressor, whatever work produced by turbine is used to be absorbed by compressor. So WT will be equal to WC. So if that happens, what happens? Network is
0.
0. So under what condition you keep WT equal to WC and tell me under what condition it will become 0? What is the value of C?
C equal to T.
C equal to T. Okay. So here also it will become 0. So T into 1 minus 1 by C is equal to C minus 1. So T into C minus 1 by C is equal to C minus 1. C minus 1, C minus 1 goes up. So T equal to C, like this. Okay. Now, if this is 0 at 2 points, what it means? How will be the variation in between?
Curvilinear.
It should be
Increasing, then
and
decreasing.
decreasing, right? It should be increasing and decreasing. In what fashion, I don't know, but definitely it will be increasing and decreasing, and there should be some peak. Am I right or not?
Yes, sir.
Right? So, what is the peak? That is the optimum C. Can you find out what is the optimum C? What should I do?
Differentiate.
Differentiate this with respect to C. So, D of W net by CPT1 by DC is equal to 0. Can you tell me what is the value of C?
Root T, sir.
Yeah, root T. C optimum is equal to root T. How? You just differentiate. So T minus T by C minus C plus 1, right? So differentiate. So the differentiation of this is 0 and differentiation of this is T by C square. And so minus 1 is equal to 0 like this. So T by C square is equal to 1 and C square equal to 2, T and C equal to root T. Okay, so that is the optimum C. So root T will be maybe somewhere here. It will not be at the center, right? It will be somewhere towards 1. And suppose some T is equal to 4. Then what is root T? 2. Okay, so if this is 2, 1, this is 2, and this is 3, and this is 4. So optimum will be, suppose if my T3 maximum temperature is 1200 Kelvin, and T1 always usually be 300 Kelvin because it is room temperature. So then small t equal to 4. So if I take that particular one, then I will get something like this, where peak will be at 2. Am I clear about it?
Yes, sir.
Yeah. Okay, so now suppose I go to higher temperatures, maybe T3 is equal to 1500. Then small t is 5, right? And so the point will be here, and the root 5 will be more than 2. So it comes something like this. Okay, this is for t equal to 4, this is t equal to 5. In the same way, I can get like this. This is increasing the values of t. Am I clear about it?
Yes, sir.
So T optimum moves towards right as T increase. Okay, so because T maximum also, C maximum also, sorry, C optimum, right? C optimum moves towards right. And C maximum also moves more towards right. Okay, so like that. This is the dependency of work done on C and T. So there is increase and decrease, but efficiency, it continuously increases. Whatever be the value of T, because it is independent of T. Eta is equal to 1 minus 1 by C. It is independent of T. But W depends both T and C. Am I clear? Okay. At C optimum is equal to root T. That is root T3 by T1. Right? And so actually C is equal to T2 by T1, which is equal to T3 by T4. Okay, so because C equal to root T, C square equal to T. Means what I will do is C square, T2 by T1 is 1C, T3 by T1 is, T3 by T4. Okay. Yeah. Okay, so T2 by T1 is 1C, T3 by T4 is 1C. So this is C square. C square is equal to T, means T3 by T1. Am I right? So what happens now? T3 gets cancelled, T1 gets cancelled, and T2 will be equal to T4. Under optimum conditions, T2 will become equal to T4. See, physically, I'll discuss what happens, right? So if it is like this, and that is, this is 1, this is 2, this is 3, this is 4. So this must be approximately equal to this. Then only I will get the optimum cycle or optimum work. Am I clear? So what happens is, if this is there will be a particular R, right? So this particular R optimum is equal to C optimum to the power of gamma minus, because C is R power gamma minus 1 by gamma. So if R is greater than R optimum or R is less than R optimum, my work will reduce. Why? Because if my R is greater than R, this is R optimum like this. Suppose my R increase, and this T3 is same and T1 is same, right? If I increase the pressure ratio, so what happens? The cycle will become like this. Am I clear about it?
Yes, sir.
So what happens now here, the WC is very much. The work taken by the compressor is a very lot compared to the previous W taken the compressor work. Now you can see WT minus WC decrease. Am I right or not? So
Yes, sir.
the work is less because WC is high. The more compressor takes more amount of work from the turbine. So W net decrease. What happens if R is less than R optimum? Suppose I take here. So what happens to the cycle? It will become like this. Am I clear? Now you can see that what happens is QL very much increase. Previously QL is up to here only. So the area under this. Now QL is this much. Am I clear or not?
Yes, sir.
So in that way, again, W net decrease. So there is an optimum value of R at which I get the maximum work. If pressure ratio increases more than that, compressor takes more work. If the pressure ratio is less than R optimum, the heat loss will be more. And because of that, it happens like that. Suppose I will have, as R decrease, I have taken the extreme cases, R equal to 1 and R equal to R max. That is C max is T, right? And C max is equal to T, I told. So C is T2 by T1 and small t is T3 by T1, and under maximum condition T2 equal to T3. I will show both the extreme cases. Okay, when R equal to 1, T2 equal to T1, that is, so here the compression is just like this. Compression pressure ratio is 1, that is T1 is T2. So it becomes like this. It goes like this, comes back like this, goes like this, comes back like that. Is it clear? Network is 0. There will be heat addition, heat rejection, no compression and no expansion. Am I clear about this cycle?
Yes, sir.
So the other extreme where this T2 becomes equal to T3 means the compression is up to here like this. And there will be expansion, compression, expansion, like no heat addition, no heat rejection. This is the other extreme for the cycle where the network is 0. Is it clear?
Yes, sir.
Yeah, okay. So that is this. So when you want to have the optimum one, T2 equal to T4. So usually our pressure ratios, the practical pressure ratios are somewhat less than this optimum pressure ratio. Because if you want to have optimum pressure ratios are high, then there will be heavy machine. To withstand those pressure ratios, high pressures, I should have heavy machine. So the practical pressure ratios are somewhat less than or optimum. So what happens if less than that? So what is the negative thing with the less pressure ratios? Heat loss is more. Okay, so people thought of recovering that heat using what is called as heat exchanger. So whatever we discussed till now are called simple cycle. So when T4, this is T4, is greater than T2, I like to recover the heat lost by heat exchanger. Am I clear about it?
Yes, sir.
Yes, sir.
Okay, so next class we will discuss about what is heat exchange cycle. Okay, simple cycle in detail, we have seen all the cases and all. Just go through it. Actually, it is there in Sarvanamuthu, and it is more clear if you feel, because Indian editions are more clear sometimes. This particular chapter, you can go through Ganesh, which I am going to send. Okay. Any questions? Okay, this is what actually you have done the Bratton cycle in your BTech, but have you discussed all these this analysis? Have you done like this?
No, sir.
So these things will do a little bit extra compared to whatever you have learned in BTech. So you should not have the feeling that same thing we are studying, right? That's it. Okay, shall we have the story?
Yes, sir.
Yes, sir.
I don't know where it is. Yeah, actually, this today birthday is the great A.R. Rahman. Okay, because I am not happy that I am missing him. Okay, so today is the birthday of Rahman, and he says if music wakes you up, makes you think, heals you, then I guess the music is working. His works are noted for integrating Indian classical music with electronic music, world music, and traditional or orchestral arrangements. Among Rahman's awards are 6 National Film Awards, 2 Academy Awards, 2 Grammy Awards, a BAFTA Award, a Golden Globe Award, 15 Filmfare Awards, and 17 Filmfare Awards South. And he has been awarded the Padma Bhushan, the third highest civilian award in 2010 by the Government of India. Rahman is one of the best-selling recording artists with an estimated 150 million records sold worldwide. In 2009, he founded Sunshine Orchestra with a vision to introduce a sophisticated symphony orchestra where economically and socially deprived children get free music education by the KM Music Conservatory. Okay, so that is the great Rahman. Okay, today's story, we will see what is purpose of life. Once upon a time, there lived a wise man. He was the head of a local administration of a small village. Everyone respected him and his views and opinions were well regarded. Many people came to him seeking for advice. But his son, normally it happens like that, however, was very lazy and wasted his time sleeping and spending time with his friends. No amount of advice or threat made any difference to him. He wouldn't change at all. And the years passed, and with time faded, the youth of the wise man. As he grew older, he began to worry about his son's future. He recognized the need to give something to his son so that he can take care of himself and his family to be. And one day he called his son to his room and said, "My son, you are no more a kid now. You must learn to take responsibilities and understand life. I want you to find the real purpose of your life. And when you find it, remember it always, and you will lead a life full of happiness and joy." Then he handed his son a bag. When the son opened the bag, he was surprised to see 4 pairs of clothes, one for each season. There were also some raw food, grains, lentils, a little money, and a map. His father continued, I want you to go and find a treasure. I have drawn a map of the place where the treasure is hidden. You need to go and find it. The son loved this idea. The next day, he eagerly set out on a journey to find the treasure. He had to travel really far across borders, forests, plateaus, and mountains. Days turned into weeks and weeks turned into months. Along the way, he met a lot of people. He was helped by some with food and by some with shelter. He also came across robbers who tried to rob him. Slowly, the seasons changed, and so did the landscapes along with it. When the weather was unpleasant, he halted for the day and continued his journey when the weather cleared. Finally, after a long year, he reached his destination. It was a cliff. The map showed the treasure being placed below the cliff under the tree. Upon spotting the tree, he began to dig the ground. He searched and searched and searched around it, under it, on it, but found nothing. He spent 2 days looking and digging for the treasure. By the third day, he was so exhausted that he decided to leave. Disappointed over his father's lie, he headed back to his home. On his way back, he experienced the same changing landscapes and seasons. This time, however, he halted to enjoy the blooming flowers in spring and the dancing birds in monsoon. He stayed in places only to watch the sunset in paradise or to enjoy pleasant summer evenings. Since the supplies he carried were over by then, he learned to hunt and make arrangement for his meals. He also learned how to shoe his clothes and shelter himself. He was now able to determine the hour of the day by the position of the sun and plan his journey accordingly. He also learned how to protect himself from wild animals. He met the same people who had helped him earlier, but this time he stayed a few days with them and helped them in some or the other way to repay them. He realized how nice they were to an ordinary passerby who had nothing to offer to them in return. When he reached home, he realized it had been 2 years since he left the place. He walked straight into his father's room, and Father, he said. The father immediately jumped to his feet and hugged his son. So how was your journey, my son? Did you find the treasure? He asked. The journey was fascinating, father, but forgive me for I wasn't able to find the treasure. Maybe someday, maybe somebody took it before I reached. He surprised himself by what he just said. He wasn't angry at his father now. Instead, he was asking for forgiveness. Because actually at the beginning he was so angry, but by all this journey, he changed his attitude. And there wasn't any treasure in the very first place, my son, father answered, smiling. But why did you send me to find it then? He asked. I will surely tell you why, but first you tell me, how was your journey to the place? Did you enjoy it? Of course not, father. I had no time. I was worried someone else would find the treasure before I did. I was in a hurry to reach the cliff. But I did enjoy the journey on my way back home. I made many friends and witnessed miracles every day. I learned so many different skills and the art of survival. There was so much I learned that it made me forget the pain of not finding the treasure. And then the father said to him, exactly, my son. I want you to lead your life with a goal. But if you remain too focused on the goal, then you will miss out the real treasure of life. The truth is, life has no goal at all, other than to just experience it and grow with it every single day. Okay, that's what I was telling. Actually, it's not the destination that you have to enjoy. Okay, not the goal. Actually, you have to enjoy the journey. Every minute of the journey, every day of the journey, you have to enjoy. So that is more important. Whether you achieve your goal or not, we don't know, right? And whether we alive or not, whether the goal is there or not, whether we achieve it, that is different thing, right? But if you enjoy the journey of going towards that, right? So that is more important. Okay, thank you very much. Thank you. See you tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.